Hello everyone, welcome back. So in today's video, we'll take up the remaining problems from the Check Your Understanding section from the chapter of kinematics. So this is problem number 34. So the statement is we have two cars that are moving at constant speeds. One of them is moving on a circular path of radius 200 meters and the other is moving along a straight road. The magnitude v of velocity of one car relative to the other has been recorded at regular intervals of time, and data thus obtained is represented in a graph as shown in the figure. Calculate speeds of both the cars relative to the ground. Okay, so this is the graph that is given to us. So kind of a curved graph for the initial 20 seconds, and after that it becomes kind of straight, right? And the other half is exactly the mirror image of this half, right? Okay, so one of the particles is moving along a circle and the radii of the circle is given, and let's just say this speed is equal to v1. Okay, and another particle is moving along some arbitrary direction in a straight line. Let's just say its speed is v2 and the direction unit vector, let's just say it is a cap. Okay, so let's say the center of the circle is our origin, which means the relative velocity v12 is nothing but v1 vector minus v2 vector, and v1 vector I can write it as the magnitude v1 times theta cap. Okay, and where theta cap is the unit vector along the tangential direction, and v2 vector we can write it as v2, which is its magnitude, times a cap. So this is the relative velocity of particle 1 with respect to particle 2. Now the magnitude of this vector is what they have given us as v. So this, if you use the resultant formula, will come out to be v1 square plus v2 square minus 2 times v1 v2 times theta cap dot a cap. Okay, and the square root of this. Okay, so finally we have figured out the net relative speed of particle 1 with respect to particle 2. And the plot of this particular v is what is given to us in the y-axis. So we can also simplify it a bit more. So this theta cap dot a cap, this is the dot product of two unit vectors, right? And theta cap, once again, it is the basically the direction that is tangential to the given point, right? So we're going to take this direction as theta cap direction. A cap is a constant unit vector. So let's say it is along this direction. And let's say the angle between them at any general instant of time is theta. Okay, so which would mean that theta cap dot a cap is basically the cos of angle between them, which is cos theta. So we can also write this as cos theta. So v turns out to be v1 square plus v2 square minus 2 v1 v2 cos theta and the under root of this term. Okay, so now the thing is, guys, looking at this particular expression, we can see that the minimum of this expression will occur when cos theta equals 1. V minimum should be equal to v1 minus v2 and the modulus of this, right? And looking at the plot, we can easily see that the minimum occurs at 25 seconds and it's actually equal to 0, which means the minimum value of the speed is 0, which means there is only one possibility: v1 has to be equal to v2. Okay, so now as we have figured out that v1 equals v2, we can substitute it into our speed equation. So we get v equals, so I can take 2v square outside, and this will become 1 minus cos theta and the square root of this term. And 1 minus cos theta, we can write it as 2 sine square half the angle. So this just becomes 2v sine of theta by 2. Okay, and we need to keep in mind that sine theta by 2 is positive. So basically we have to take the modulus of this expression, right? Because we are talking about speed. But yeah, let's not care about that. So just so that we can differentiate, I'm just going to take v1 equals v2 as u instead of v. So this will become u. So now the speed is simplified as 2u sine of theta by 2. Okay, and once again, guys, this theta was the angle between both the velocity vectors. Now, okay, so now if you observe, guys, at time t equal to 25 seconds, their relative speeds is 0, which means both the velocity vectors are parallel to each other. Even the car moving in the circle will have the speed towards the right, same as the car moving along the straight line. Okay, so in this situation, as you can see, their relative speeds is 0. And from here also, you can see that in this situation, theta is 0, meaning both the velocity vectors are parallel, so the relative speed is also 0. Okay, so now the thing is, let's try to figure out dv by dt. Okay, so this is going to be u cos theta multiplied by the rate of change of angle theta. Okay, so now, guys, we took this theta as the angle between v1 and v2, but this is also the same angular velocity of this circular motion. Okay, and that we can easily prove. So initially, let's say the velocity vector is in this direction. After some time, let's say it rotates by an angle of d theta. So even this angle is going to be the same angle d theta. So basically, if the car travels along an angle of theta, the velocity vector will also rotate by the same angle theta, right? So this d theta by dt is the same as the omega of this circular motion. Okay, so we can also write it as u divided by capital R. So we're writing the omega as u by capital R, and from here we'll get the answer as u square cos theta divided by capital R. Okay, so now we have a cos theta over here. So again, as we discussed earlier, guys, the bottommost point corresponds to theta equals 0, right? So the acceleration very close to this t equal to 25 seconds should correspond to theta equal to 0 degrees. So let's figure out that acceleration. So that will be u square by capital R, right? So now using the graph, we can see that at points very close to t equal to 25, this is almost a straight line, right? V is almost a straight line. So we can roughly estimate its slope. So the height of this part is 10 units and the base is 5 units. So the slope of this part is actually 2 meters per second square, right? So basically very close to t equal to 25 seconds, the acceleration is 2 meters per second square. So from here, we can see that u square turns out to be 2 multiplied by r, which is 200. So from here, u turns out to be 20 meters per second. So which basically means both the cars are moving with a speed of 20 meters per second. So that would be the answer to this question. Now let's move to the next one. Okay, so this is problem number 35. So in this question, we have a stone that is projected from the ground with a velocity of 10 meters per second, and its trajectory is drawn to an unknown scale on a graph paper. The horizontal range and the maximum height on the graph are 1 meter and 0.25 meters respectively. So the range of the projectile is 1 meters. And the maximum height is given to be 0.25 meters. Okay, so using these two relations, guys, we can actually directly find the angle of projection, the projection angle, which r by h equals 4 upon tan theta. You can easily prove this by substituting the value of max range and maximum height. So r by h is equal to 4, right, in this case. So tan theta equals 1 or theta equals 45 degrees. Now it's given that the graph paper is glued on a horizontal tabletop. And if an insect moves along the trajectory on the graph paper with a uniform speed of 1 centimeters per second, what should be the modulus of its maximum acceleration? So again, so let's determine the trajectory. So the trajectory equation for a ground to ground projectile is y equals x tan theta times 1 minus x by r. And this equation is assuming the initial point of projection as the origin. Okay. So now let's substitute the values in. So we get tan theta is 1. So it will be x times 1 minus x, which would be x minus x squared. So the plot would look something like this, and the roots of the parabola are x equal to 0 and x equal to 1. Now it's given that, guys, this is plotted on a graph paper and it's kept on a horizontal table, and it's given that an insect is walking on this trajectory, this parabolic trajectory, with a uniform speed of 1 centimeters per second. Okay, so its speed is given to be constant and is equal to 1 centimeters per second. So the tangential acceleration in this case is 0. So now they're asking us what should be the modulus of maximum acceleration. So here we'll use a direct result of curvilinear motion. So whenever we have a particle that is moving along a curve, the direction along its velocity vector is called the tangential direction, and let's just mark it as t cap, and the direction normal to the tangential direction is what we call as n cap, or normal direction, right? So in this question, the acceleration along the tangential direction is 0 because the speed is given to be constant, and the acceleration in the normal direction is given as the speed squared divided by the radii of curvature at this particular point. So if we take a small arc at this particular point, this arc is going to be part of a circle. So the radius of this particular circle is what we call as rho. So v square divided by that radii of curvature will give us the normal acceleration at that particular point. So basically we have to figure out when is the normal acceleration maximum. So the speed of the particle is a constant. So we have to minimize the denominator. So we have to figure out the point on the parabola which has the smallest radii of curvature. So we'll use the formula of figuring out the radii of curvature of a random curve, right? So the formula for figuring out the radii of curvature of any curve was 1 plus slope squared to the power 3 by 2 divided by the double derivative and its magnitude. Okay, so this is the formula with which we figure out the curvature radius of any curve y equal to f of x at any particular point. Okay, in the given equation, our curve is a parabola. So the equation is y equals x minus x squared. So if you observe, the double derivative actually turns out to be a constant in the case of this kind of a parabola, and it turns out to be minus 2, right? So if I just substitute it over here, so this just becomes 1 plus slope squared to the power 3 by 2 divided by 2. Okay, so now we want to figure out where is the slope minimum, and that is pretty straightforward by looking at the function. It will be minimum when y dash square is minimum, and y dash square has a minimum value of 0, right? It's a positive quantity, so it should be greater than or equal to 0. So rho will be minimum where y dash is equal to 0. Now y dash is equal to 0 when we have a maxima or a minima. So basically the radii of curvature will be maximum near the maxima. Okay, so near the maxima of this parabola. So this is the point where the radii of curvature is maximum. So now we'll just substitute the slope to be 0. So we'll get the radii of curvature as half meters. So the normal acceleration in this case comes out to be v square divided by rho, which is 2 times 10 to the power minus 4 meters per second square. Okay, so that was it for this question. Now let's move on to the next question. Okay guys, so this is the last problem of the check section. So this problem is again related to chasing, right? And this question has a lot of parts in it that we have to solve. So we have a particle P that is moving with a constant speed of u on a straight line that makes an angle of theta with the positive x direction of a coordinate system. When this particle crosses the y-axis at a point of 0, L. So the particle P, it moves with a constant speed along a straight line and it cuts the y-axis at 0, L. So the trajectory will look something like this, right? And it moves with a speed of u and it makes an angle of theta with the horizontal. Now when the particle P crosses the y-axis, meaning when it is at this point, another particle Q starts from the origin and chases point P with a uniform speed of v. And it's given that v is greater than u. And guys, in chasing problems, so let's just say a cat is trying to catch a mouse, and if the cat's speed is greater than the mouse speed, then the cat will catch the cat. Then the cat will catch the mouse after some time. And if the cat's speed is less than the mouse speed, then the cat won't be able to catch the mouse. Okay, we'll try to observe that by looking at the equations. But yeah, it's given that the chaser or the cat Q always maintains its velocity vector towards the chased P. The mouse is going to move along a straight line. The cat, let's say after some time, it is somewhere over here. And let's say the mouse is at this point X. So the cat's velocity vector will be in this direction. So the head of the velocity vector will always be pointing towards the mouse, is what they're trying to say. So that's what they're trying to say with the last sentence. So in the first question, they're saying how long after Q starts from the origin will it catch P? So basically we have to figure out the time of catching. Okay. And in the second question, they are slightly modifying the situation and we are saying the cat and mouse both have a speed of v. So basically our mouse is present over here at 0, L, and this line makes an angle of theta with the horizontal once again. And the cat is actually present at the origin. Okay, and it is about to chase the mouse. So now let's just rotate this situation by theta degrees clockwise so that u vector appears horizontal. So now we have the mouse over here and it is about to move towards the right with a speed of u. The cat will be somewhere over here right now, and the distance OA is actually equal to L. Okay, and this angle over here is going to be theta. Okay, and how is it theta? Because we rotated the entire thing clockwise by theta degrees, right? So this line OA was initially vertical. So after rotating it by theta degrees, even line OA will rotate by theta degrees, right? So this is how the situation is looking like, basically. Okay. Now again, the cat's velocity vector is towards the point A and it will have a magnitude of V. So now this is pretty similar to the common chasing problem. It just has some slight differences, right? Okay. So let's say after some time, guys, the cat reaches this point A and the mouse would have obviously covered some distance forward. So let's say it's somewhere over here now, okay, at the point B, and it's constantly moving towards the right with a speed of U. And the cat's velocity vector is directed in the direction AB, okay. So his velocity vector is along this direction AB and its magnitude is V. Okay, so now as we know that V is always along AB, let's call the distance AB as small r. And let's just say the angle that r makes with the horizontal at any general time is theta. Okay, so basically if I separate out this line AB, then the point B is moving horizontally with a speed of u and the velocity of point A is V. Okay, so if I extend this line out a bit, this angle is also theta. So from here, dr by dt, which is the rate of change of the length AB, equals, so the component u cos theta is trying to increase the length AB. So this would be equal to u cos theta minus V. Why? Because V is trying to reduce the length. So this is our equation number 1. So let's just bring it to the next page. So let's try to solve it a little bit. So dr is equal to u cos theta dt minus v dt. So now let's solve this integral. So u and v are both constants, so we can take it out of the integral. At time t equal to 0, the value of r will be again guys, the value of r is the distance between the cat and mouse. And initially at time t equal to 0, this was the situation, and the distance between both of them was equal to L, right? So initial value of r is L, and when chase is complete, the distance between them would become 0, because in this case, when v is greater than u, the cat actually catches the mouse, and when it catches the mouse, the distance between them is 0, right? So from here, L turns out to be vt minus u times integral of cos theta dt from 0 to capital T. So again, we don't know how theta varies with time, so we cannot compute this integral, but we can easily determine the cos theta integral by equating the horizontal displacements. So if you observe guys, initially this was the situation, and finally what will happen is the cat and mouse both will come at the same point, right? So the displacement covered by the mouse is this arrow over here, and the horizontal displacement of the cat is this vector over here. So if you look at the difference in length, it will turn out to be this dotted green arrow. Okay, so the mouse starts from this particular point, and let's say it's caught at this point x. So this total distance is going to be u into t, because the mouse is running with constant speed, right? And the horizontal speed of the cat is going to be v times cos theta, right? Theta is the angle v makes with the horizontal, so the speed in the horizontal direction is v cos theta. So, but as it is a variable quantity, we have to integrate v cos theta with respect to time to get the horizontal displacement of the cat. If you do v cos theta dt, you will get the distance ox. Okay, so this is also equal to, let's just write it as ox. Okay, so this complete distance over here is what is distance ox. Now what is this green dotted length, guys? So this length was equal to L. So this length is going to be L sine. Actually guys, we took theta in both cases, right? This angle, let's just say it is theta naught. Okay, just so that we don't confuse it with the variable theta. So this length is going to be L sine theta naught. Okay, the distance ox is nothing but L sine theta naught plus ut. Okay, so we can write this as L sine theta naught plus u capital T. Okay, so from here, as you guys can see, we can easily figure out the integral cos theta dt, right? Okay, so once you substitute and rearrange, you'll figure out the time t as this particular value. Okay, so this is the answer to question A. Okay, so now in the question B, what they're saying is that both the cat and mouse have the same speed. Okay, then what will be the minimum distance between them, and what will be the maximum magnitude of acceleration of the chaser? Okay, so guys, this case is just a slight modification of the previous case, but the difference here is that now A and B both have the same speed. Okay, so guys, if both of them have the same speed, then B will never be able to catch A. So let's try to understand why is that. So B's trajectory again is going to look something like this, and finally after some time it will reach the white line, and once it reaches the white line, it will move horizontally. Why? Because when it reaches the white line, the mouse is right in front of it, right? So its velocity vector will be towards the right. So once it reaches the white line, it will move horizontally. So let's say after some time t, B reaches somewhere over here. This is the new position of B, or the mouse. Let's just write it as cat. So the cat reaches this point. So the claim I'm making is that the mouse will be in front of the cat. Okay, and the reason for that is pretty obvious, guys, because throughout the motion of the cat, the horizontal speed is going to be u cos theta, right? Where theta is the angle that we discussed earlier, right? Now u cos theta is clearly less than u, which basically means throughout the motion, the speed of the mouse was greater in the x direction, which means it will cover a greater distance, right? Okay, and on top of that, it already had a lead over the cat, right? It was already in front by some distance. So that distance plus it having a greater speed just means that the mouse will be way ahead of the cat. So finally, the situation would look something like this. So the mouse in this case will have a speed of u. The cat will also have a speed of u. And now the separation between the cat and mouse will not change. So finally, let's say the separation between the cat and mouse is r0. So this r0 is going to be the minimum separation. Why? Because if you remember, dr by dt, guys, was u cos theta minus v. So in this case, v is equal to u. So this will be u times cos theta minus 1. So here again, guys, theta is the angle, cat is the angle the cat's velocity vector makes with the horizontal. So cos theta is obviously less than 1, which means it is negative, which means the length r will reduce with respect to time. Okay, and it will keep reducing. So the distance r will keep reducing till the cat reaches the white line. After this point, theta is 0 degrees. Theta is 0, which means the rate of change is 0. And that we can see from the diagram as well, right? After reaching this situation, the cat and mouse's distance will be r0 itself. So yeah, this r0 is the minimum separation between the cat and mouse throughout their journey. So this is the original equation we wrote for the previous question. The only difference here will be that for the final separation, instead of 0, it will be r0. And v is equal to u. Other than that, everything remains the same. Okay. Again, we'll use the same trick for the horizontal displacement to figure out the cos theta integral. Okay, so the displacement of the cat is going to be this vector over here, right? And the displacement of the mouse is going to be this vector. So the displacement of the mouse is simply u times capital T, right? The initial separation between B and A is again L0 sine theta, just like in the previous problem. Horizontal displacement of the cat, we can write it as speed in the x direction, which is u cos theta times dt from 0 to capital T. So now all we have to do is equate the distances. So the integral of u cos theta dt plus r0. So if you do u cos theta dt plus r0, you'll get the distance from this point B to the final position of the mouse. Okay. So another way of writing this is L0 sine theta plus ut. This would be equal to L0 sine theta plus ut. So we are basically just equating distances at this point. And from here we can easily get the integral of u cos theta dt. Okay, so now we can just substitute the integral u cos theta dt to our original relation. And from here r0 turns out to be L0 1 plus sine theta naught divided by. So this r0 is the final separation between the cat and mouse. So now they also asked us about the acceleration of the chaser. So now let's talk about the acceleration. So why is there acceleration in the first place? So once again, guys, the cat's motion is going to be a curvilinear. The cat, as you guys can see, it's going to take a curvilinear path, right? And whenever we have a curvilinear path, as we observed in the previous problem, there is going to be tangential acceleration and normal acceleration in the most general case. And in this case, the tangential acceleration is 0 because both cat and mouse are running with constant speed, right? But the cat, as it is changing its direction, it will definitely have a normal acceleration at each point. So that normal acceleration is what we have to find. More specifically, we have to find out the maximum value of that acceleration. Okay. So at some general time t, let's say the mouse is over here and the cat is at this particular point. Okay. So mouse, let's say, is m, cat, let's say it's c. The line connecting them is what we called as r, and the angle it makes with the horizontal is theta. So if you observe, if you break u into two components, one component will be perpendicular to this line CM. So that component is going to be u sine theta, and the component along the line CM is u cos theta, right? So from this, what we can see is the value of d theta by dt, which is again the omega of this line CM, is going to be u sine theta, which is the perpendicular velocity of this point m, divided by the length CM, which is r. Basically, with respect to this point C, we are seeing how is the line CM rotating. Okay, so that is nothing but the perpendicular velocity of the point M divided by the distance. Okay, yes, the C point will have some velocity V along the line CM, but that doesn't contribute to the rotation of the line, right? Only this u sine theta component rotates the line. Okay, so now we also have to put a negative sign over here. Why? Because the omega is trying to decrease the angle theta. It's opposite to the direction of theta. So what we figured out here, guys, is the omega of this line CM. Okay, so omega of the line CM is equal to d theta by dt. This is also equal to omega of v vector. Why? Because v vector is basically the velocity of the cat. The cat's velocity vector is also along the line CM. After some time, the point M will move forward and the C point will come somewhere over here. And this is the new CM vector. And as you can see, it has rotated by some angle theta. Okay, and here also, if you observe, the velocity vector of the cat is in the CM direction. So the cat's velocity vector rotates exactly like how the CM line is rotating. Therefore, we can say the omega of the v vector is the same as the omega of the line CM. So they're both equal in terms of magnitude. So now again, we have to comment on the acceleration of the cat, right? So for that, we need to observe how is the velocity vector changing. So the velocity vector, let's say initially it was in this direction, okay? And the magnitude of the cat in this case is u, right? And after some time, as you guys can see, it is going to turn in the clockwise sense, right? So now the velocity vector has turned in the clockwise sense by a bit. And now let's say this is the new velocity vector. Its length will not change. Magnitude remains the same. So it's still u. And let's say it has rotated clockwise by a small angle of d theta. So within this small change d theta, the change in the velocity vector is what is the acceleration. So within this small angle d theta, now as a change in velocity vector is the final velocity vector minus the initial velocity vector. So that is this vector over here. So let's say this is dv vector. So let's say this has a magnitude of. So this dv by dt is what is the normal acceleration. dv vector is perpendicular to the u vector. So u vector plus dv vector will give you the final velocity vector. Now if dv was not perpendicular, it will also have a tangential component, which means the magnitude of u would change, right? But we know u is constant, so dv has to be perpendicular to u. Again, this is the normal acceleration, and using the arc length formula, we can say dv is going to be u d theta. Okay, so arc length is equal to radius times the angle. So now all we have to do is divide by dt on both sides. So we can say dv by dt is u times. So here once again guys, d theta by dt is the rate at which u vector is rotating. In this question, u vector is rotating in the same sense as the cm vector is rotating. Therefore, we can say this d theta by dt is in terms of magnitude also equal to u sine theta by r. So finally the acceleration, normal acceleration of the cat turns out to be u multiplied by omega, which is u square sine theta divided by r. So in question A, if you wanted to figure out the acceleration, it would be uv sine theta by r, because the cat's speed in that case was v, right? So yeah, now we finally figured out the normal acceleration, but the question isn't done here. We have to figure out the maxima of this expression. Now here we have two variable quantities, guys. We have sine theta here, and we also have r here. So we need to eliminate one of them. Only then we will be able to figure out the maxima of this function, right? In this question, we actually have to figure out the value of r. So again, we have to go back to our original configuration. So yeah, so basically we have to figure out r with respect to time. So we'll just modify our equations a little bit. Time of catching, we'll just integrate to a general time t, and at any general time t, we'll say the distance between them is small r. Okay, now again for the displacement equation also, we'll just integrate it to small t, and then we'll observe. But here you have to pay attention to something. So let's just redraw the diagram a little bit. So in this case, guys, let's say the mouse is at this point m. So the displacement of the mouse, so the distance am is going to be u times small t, right? And let's just say the cat is at this particular point c. The distance cm is what we are defining as small r, and this angle over here is theta. Integral u cos theta dt from 0 to small t will give the horizontal displacement bc, okay? This distance is what integral u cos theta dt will give us, okay? So this displacement plus r cos theta is equal to bm. Okay, that is the distance between b and m. So if I add another distance of r cos theta to our u cos theta dt, I'll get bm distance. Okay. Now for the mouse, we can also write bm as L0 sine theta plus ut. Okay, so we'll just get rid of the r0 from here. So this is the expression for u cos theta dt. Okay, and ut, instead of u capital T, we'll just write it as u small t. Okay, so this is basically the modified expression. So now what we'll do is we'll pick up u cos theta dt from here, substitute into this expression, and figure out r as a function of theta. After substituting, this is what we get. So the ut cancels out, and we'll get r equals 1 plus sine theta naught divided by 1 plus cos theta. Now once again, guys, this theta naught is a constant. This is the initial angle theta, okay, and this cos theta is the variable. So now we can substitute this value of r into our acceleration expression, and we'll get the acceleration as u square sine theta times 1 plus cos theta divided by L multiplied by 1 plus sine of theta naught. So this is, as you can see, the acceleration, we finally broke it down into just a function of theta. So this is some constant multiplied by a function of theta, and the function of theta is sine theta plus sine theta cos theta, and sine theta cos theta I can write it as sine 2 theta divided by 2, right? So basically we have to maximize this function, so we'll just differentiate it with respect to time. So this will become cos theta plus cos 2 theta, right? So this is the derivative. Okay, so this is using cos c plus cos d. We can write as 2 cos of 3 theta by 2 times cos of theta by 2, and we want this to be equal to 0, that to get the maxima condition. So one possible way is cos theta by 2 equal to 0, which means theta by 2 should be an odd multiple of pi by 2. And from here, theta needs to be an odd multiple of pi, which is not correct, because if theta is an odd multiple of pi, acceleration would be 0, right? Sine 2n plus 1 pi would be 0, which means it's the other alternative. So, and the other option was 3 theta by 2 should be an odd multiple of pi by 2. This implies theta is an odd multiple of pi by 3. So we'll take the most simplest case from here, that is theta equals 60 degrees, and we'll substitute it into our acceleration expression. So A max will just turn out to be, okay, so once you substitute the value of theta as 60 degrees, guys, you'll get the acceleration as this particular value. Okay, so that was the solution to this question, guys. If you have any doubts,